Hello students, in the last video we have stumbled upon one concept where we could not proceed when we came to let us go to the last video's last slide. So here if you look at this particular concept, we actually stopped while computing, and why we stopped while computing is because we didn't have enough information on how to write t is equal to something given this equation. So what we did, we found a escape out by plotting the lines across x and y axis, horizontal and vertical lines, and figured out that the answer is 8 minutes, and that is how we concluded this is 8 minutes. Now when we start such a thing analytically, that is RT is given to be equal to 30, what is the value of t? We want to answer such questions, then we need to look at the function r and we need to understand whether this function r is reversible or not, which is the case in this particular function, because we were able to map it uniquely. So what are the important traits of this function RT? RT was a one-to-one function and it was increasing function, hence it was 1 to 1. Therefore we were able to find a reversal of the value 30 to the value of t, which is 8. So in order to find such reversible functions, we need to understand the theory which we will discuss now, is the theory of inverse functions. So when I talk about inverse functions, I am talking about functions from domain, which is real line, codomain, which is real line. Okay, so a function is defined from real line to real line. Then the immediate question that comes to our mind, are all functions reversible? And the immediate answer is a very well known function that we have seen, is f of x is equal to x square. Now this function is not reversible because it fails to pass the horizontal line test, if you remember. So y is equal to x square, if I try to plot, it will be something like this, very close to something like this, and when I pass a horizontal line through this, it passes through 2 points, and let these points be 2 and -2, and that essentially means this when I feed in the value 2, it will give you 4, and when I feed in the value -2, it will give you the answer to be equal to 4. Now if this function is reversible, when I feed the value 4, it can spit out the two values 2 and -2, so it is not uniquely spitting out the value. Therefore this function is termed as not reversible function. Such functions we cannot study the inverse properties or the properties of inverse functions. However, if you restrict the domain of this function instead of real line to only positive half of the real line, then you will get a one-to-one correspondence between the values on x-axis and y-axis, and then you can talk about inverse of these functions when it is defined from 0 to infinity. Now let us look, then the question is, okay, this function is not reversible, then which functions are reversible? That is a question that we can ask now. In order to answer this question, we need to study some class of functions. So in last few videos we have already seen that one-to-one functions are nice functions. Any function that is either increasing or decreasing is one-to-one, and therefore we can look at one-to-one functions for the class of reversible functions. So here is our answer, that we will start looking at the class of one-to-one functions. Let us look at a simple function, a linear function, g of x is equal to 4x. Is this function reversible or not? Right. So in order to answer this question, let us look at g of x is equal to 4x. So you can put y is equal to 4x. Right. If you look at y is equal to 4x, from our basic understanding of linear equations, or rather than linear equations, an equation of a straight line, this is a straight line passing through origin having slope 4, right? So if I want to find a point x on this axis, then I will simply transform this as y by 4 is equal to x, and this transformation is unique. Therefore I can write some function, let us say r of x, as x by 4, and this function will actually be giving me the inverse of this. So let us take this function. If this function h of x is equal to x by h of x is equal to x by 4, so I don't need to write r of x is equal to y by 4, h of x is equal to x by 4. Now if I start with this function and I want to get the value of x, what should I do? I will write y, okay, so I will write y is equal to x by 4, and in that case I will get 4y is equal to x, and therefore I will get another function which is say s of x, which is equal to 4 times x. So essentially what we have seen is this g of x and h of x have something in common. So let us recollect the notion of composition of two functions and try to answer this question. For example, if I consider the function g o h of x, okay, now this function is again a function and it will simply operate like g of h of x, and once you start with g of h of x, what you will do is you will treat h of x as an argument of g and put the values of h of x inside. Okay, so let us try to understand this. So it is like g of h of x is actually, what is g of x? 4 of x, right? So it will be 4 times h of x. Now what is h of x? H of x is nothing but x by 4. So 4 times x by 4, which will give me x. So what this function is? This function actually gives me identity function GOH of x is equal to x. And in a similar manner, I can start thinking about HOG, HOG of x. Now in this case, if you recollect the notion of composition of functions studied in week 1, h of g of x, correct? So if h of g of x, I will simply see what is h of x. It is g of x by 4, and therefore what is g of x? It is 4x. Therefore I will get 4x by 4, which is actually equal to x, and therefore this is also equal to identity function of x. So now to summarize, what I got is GOH of x is equal to I of x, which is equal to HOG of x. Now this becomes our definition of inverse function, and let us define it formally as the definition of inverse function. So here is a definition of inverse function. The inverse of a function f, we denote it by f inverse, is actually a function. This is our notation. F inverse is actually a function such that f inverse of f of x, or I can rewrite this as f inverse O f of x is equal to x. Now here is a typical thing that comes for all x belonging to domain of f, which is equal to range of f inverse, and FOF inverse, or you can write this as FOF inverse of x being equal to f inverse of x is equal to x for all x belonging to domain of f inverse and range of f inverse. So right now when I did this particular calculation, I have assumed that everything goes from real line to real line. There was no such event because this function is defined from real line to real line, and this function is also defined from real line to real line. So there was no consideration for domain and ranges. But sometimes it may so happen that your original function may be defined, let us say f is defined from R to 0 infinity. If such a definition is there, then you need to worry about the domain of a function and the range of a function, because here the domain of f is R and range of f is 0 infinity, right? So if I talk about f inverse of this, then naturally I cannot go over entire real line. I have to go over 0 infinity and then I have to come to R, right? So this is how it will be defined, and therefore the domain of f will become, the range of f will become the domain of f, and the domain of f will become the range of f inverse. This is the typical factor that you need to always remember. Now let us go ahead and improve our understanding about one-to-one functions. So if the given function is one-to-one function, then f inverse always exists for f. Now the notation may confuse you, so let me give you one precise warning that the notation f inverse does not mean 1 by f. This is very important because you may quite often confuse f inverse with 1 by f. So whenever we want to discuss in this course or in mathematics, whenever we talk about f inverse of x, it simply means it's an inverse function. Okay, so this is an inverse function, and whenever you want to talk about the 1 by f, then you should talk about f of x minus inverse. So this f of x minus inverse is 1 by x, and this f inverse is actually has a meaning f inverse of x. So this you always remember. Now if f is one-to-one function, f inverse always exists for f. This you have to trust me. I cannot prove it right now with the current tools. So f inverse always exists. Let us take one example. G of x is equal to x cube and g inverse of x is cube root of x. This you can write as x raised to 1 by 3 as well. So that it is simple to verify. Okay, so now you want to verify that the given functions are actually inverses of each other. So in this case, let us first identify the domains. It's a real line to real, and the range is real line. So naturally for inverse also it's real line to real line. No question about it. So let us talk about g inverse g of x. Now if you recollect the definition of inverse function, then naturally the inverse function is a function such that all these combinations should produce x, f inverse f of x or f inverse of x, right? So let us talk about g inverse of g of x. So let us keep g inverse intact and put what is g of x, which is x cube. Okay, now this you substitute the function g inverse of x as x raised to 1 by 3, then this becomes x cube raised to 1 by 3, then multiplication of indices a raised to mn applicable, so it will be x. Okay, so one way it is true. Now the second way also you have to check. So what you will do now is you just write g. Within the box you write g inverse of x. What is g inverse of x here? X raised to 1 by 3, and then simply put the function g. So x raised to 1 by 3, the whole thing raised to 3, which again a raised to mn. So this will also give you x. Domain and ranges we have already seen. So whatever the conditions of that, therefore G and G inverse are inverses of each other. So G inverse is inverse of G. Okay. Let us take this example where we are supposed to verify whether F and G are inverses of each other. Okay. So let us try to verify. You can check the domain and code ranges of these functions. I will simply start with F of G of X. Fine. So if I start with F of G of X, as per our notion, what we will do, we will simply keep this Gx in place wherever F has an argument X. So we will take this and we will put Gx wherever X is written there. So let us do that exercise. That is G of X minus 5 upon 2 times G of X plus 3. Okay, this is F O G of X. Now what is G of X? G of X is this. So let us go ahead and substitute those values over those functions in place of G of X. So it is 3x plus 5 upon 1 minus 2x minus 5 upon 2 times 3x plus 5 upon 1 minus 2x plus 3. Correct? So now it's a matter of pure algebra. Just simplify this. So denominator both have 1 minus 2x in common. So multiply the numerator by 1 minus 2x and denominator by 1 minus 2x so that we will get rid of this. So it will be 3x plus 5 minus 5 into 1 minus 2x upon 2 times 3x plus 5 plus 3 times 1 minus 2x. So what is the question? We have to verify that F is the inverse of G. So essentially I want to come up with a number with a function which is X. F O G of X is to be equal to X. This is my end goal. Just remember this. Now you can simply simplify this. 3x plus 5 minus 5 will get rid of this plus 5. Let me change the color over here. So this will get, this one will get rid of this. Then this is minus 2x minus 10x and minus 10x will become plus 10x because of this minus sign, and then 3. So I will simply get here 13x. Now you look at the denominator, which is 2 into 3x, that is 6x. Then look at the corresponding term here, minus 6x. So this terms corresponding to x will vanish, and 3 and 2 into 5, 10. So I will get the denominator to be equal to 13, and that will give me x as my answer. So F O G of X is verified. Does this complete? Will this complete our verification of whether F is the inverse of G? No, because I want to check whether G is also the inverse of F. Then only the verification will be complete. So let us go ahead and do that. That is, we will consider G F of X, and that should give me X. That is my end goal. So now you look at what is a function G and put Fx as it is everywhere. So it is 3 times Fx plus 5 upon 1 minus 2 times Fx. What is the next step? Take the functional form of Fx and substitute it in the expression. So 3 into x minus 5 upon 2x plus 3 plus 5 upon 1 minus 2 times x minus 5 upon 2x plus 3, and then again the same logic applies. Multiply both sides by the denominator 2x plus 3, and then you will get 3 times x minus 5 plus 5 times 2x plus 3 to be upon 1 is there, so 2x plus 3 as it is, minus 2 into x minus 5. Let us look at the simplified form. Let me change the color. So 3x plus 10x, that will give me 13x. Here 3 into 5 15 minus 15 plus 5 into 3 plus 15. So this is taken care of, vanished. Upon, again the same logic applies, 2x minus 2x will vanish, 2 into 5 will give me 10 and this 3 will give me 13. Therefore I got this. Domain and ranges you have already verified for yourself, and therefore the verification process is now complete, because FOG of x is x, GOF of x is again x. So we can verify that f is the inverse of g as stated. Okay, so this completes our discussion on inverse functions. Now it is important to understand graphically what the inverse function is, or what is how the graph of f and f inverse changes. So we already have a vague understanding of the graph of f and f inverse. Now let us look at it formally. So if I know something about f or the graph of f, then given a value of a, I am able to calculate f of a, and f of a is the pair which we call as graph of x, graph of f. You look at f inverse. What happens when you talk about f inverse? Here f of a is actually on y axis and a is on x axis. So when you look at the inverse function, the values on y axis actually get converted into values of x axis, and the values on x axis will actually get converted into values on y axis. So this is the mapping that we have given. So if you start with f of a, which is y, then you will talk about f inverse of y, and when you talk about f inverse of y, you will actually get it to be equal to a, because y is equal to f of a, and this is how the entire circle is complete. So in particular, if a and fa is on the graph of f, then fa comma a is the graph of f inverse. That's obvious. So let us imagine this is the graph. This is the graph of a straight line a fa. So you plot a line y is equal to x here. This is a line y is equal to x, and this is a point which is on the graph of fx. So now you are saying that where will this point be when I talk about f inverse? So then we are also answering this question that wherever a was there, it will be f of a now, and wherever f of a was there, now there will be a, right? So in this case, you just take this distance and you plot it, you just take the distance on the y axis and choose the distance on x axis here, okay, and take the distance on x axis for this point and put that distance over here. That means it will be somewhere here, and therefore the point will be somewhere here, and this point is actually f of a comma a. So what we are actually doing when we are plotting the graph is actually we are reflecting our original function. If the original function is somewhat like this, let us say it's somewhat like this, then what we are doing is we are actually reflecting it along y axis, and it will be a very similar function which will look like this. So this is how the graph of inverse function will look like. It is actually a reflection along y is equal to x, or reflection along a function y f of x is equal to x. So in particular, the graphs of f and f inverse are symmetric across the line y is equal to x. This is what you have to remember all the time. If you want, you can prove the theorem, but there is nothing, it's just a graphical proof that if I want to compute this particular point, and if I know that there is the inverse of this function exists, then you just take the length on y and plot it across x, and length of y, length in x direction, plot it across y direction. That is what I did, and this is actually the proof of the theorem that the graphs of f and f inverse are symmetric on y is equal to x line. That completes our topic of inverse function. In the next video, we will deal with the inverse functions in a more restricted manner, that is inverse of these exponential functions. Okay.